Welcome. In this video, we're going to define what a combination is. The number of unordered, that is unarranged selections of R things out of n distinct objects is called an R combination. So in the case of a combination, you ignore ordering of your objects. You say it doesn't matter. Now, how can we show this is the case? Well, suppose we wanted to find the permutation of our objects out of n things, so order did matter. So if we wanted to find the permutation, of our objects out of n things, well, what does that equal? We could first choose our objects without regard to order. So we could say choose R things out of n items. And then we have to multiply that, again, that's because of the product rule, by the number of ways to permute those objects. So that would be permuting those R objects out of R things. Well, let's see what this looks like. Well, on the left-hand side here, we'd have n factorial over n minus r factorial. And on the right-hand side, we have n choose r times r factorial over r minus r factorial. Now, how can we simplify that? I quickly added a parenthesis that I was missing right here. And at this point, this is just algebraic manipulation. There's nothing special going on here besides messing around with algebra. R minus r is just 0 here in our numerator. And 0 factorial is 1. And in case you're wondering why, well, in how many ways can I line up 0 objects? Just 1. Don't do it. So we end up with n factorial in our numerator, r factorial in our denominator, and the product of that with n minus r factorial. So the number of ways to choose r items out of n things without regard to order is called a combination, and it can be computed using this formula. Now we can also simplify this a little bit. So here I have n choose r, and I have n factorial over r factorial, n minus r factorial on the right. Well, let's start working out what we actually have. So this is n times n minus 1 times, and I'm going to leave the numerator as is right now. There's a lot more there. I need to make more space to start with, but I also want to show what's happening in the denominator. In my denominator, of course, I have an r factorial, and I think I'm not going to expand that at all. I'm just going to leave that, and you'll see why in a second. I also have n minus r factorial, so this would be n minus r times n minus r minus 1 times, and we'd go all the way down to 1. And this would be how to expand n minus r factorial. Well, at some point, if we're starting with n, and remember, n is larger than r, at some point, you're going to end up with n minus r in your factorial. So I'm going to write that here. And after that, of course, you'll have n minus r minus 1 times dot, 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 times 2 times 1. But what number do you have right before n minus r? Let's add 1 to this. If we add 1 to this, we end up with n minus r plus 1. And so in my numerator, I have n times n minus 1. All the numbers, or excuse me, all the integers I could possibly multiply between n minus 1 and n minus r plus 1. And then suddenly I have this, and I'll highlight it. These two are the same. And in fact, this is just n minus r factorial. So I can simplify this. That is, I can simplify n choose r to n times n minus 1, multiplied all the way through to n minus r plus 1, divided by r factorial.